Hi, I'm Jack Cole with Mindware Consulting, a business focused on brain training games, such as the popular app Mind Games, and self-help apps such as Night Owl Sleep Coach, a self-help program that helps with insomnia. For the past few months, I've been conducting numerous experiments in machine learning, trying to make progress towards solving a difficult challenge called the abstraction and reasoning challenge. And to give you a little bit of an idea what ARC is it's a series of visual puzzles, and in each puzzle you have to figure out what is the concept to go from a initial example to an answer for that example. And so if you look at the first item here, you see that it goes from a 3 by 3 grid where there are horizontal lines, and just simply transferring like one of the vertical rows is the answer. And if you look at the second one, it would be like transferring one of the horizontal rows. So basically it is you look to see what direction the lines are pointing, and then you replicate a cross section of that. And when you go to the last one in the top row, you see that we have a condensing of the color into one color. And actually, I think this one is an error, and that those last two items should be just one color. And so you see on the fourth one that it has the same pattern where the two are condensed down into one, and the same on the fourth. And so ultimately, the answer, you would have to make it into the right size. And so for this one, it would be a 5 item response, and they would all be condensed down. Okay, and so what I've done in my research is I've trained over 100 machine learning models to study the problem and to get a better feel for how well transformers can perform on this type of a task. And I also have interacted with the community on Yannick Kilcher's Discord server, and I've developed an architecture that I'm hoping will make progress towards solving ARC. And ARC is a very difficult challenge that, although it was completed a couple of years ago on Kaggle, little progress has been made in applying machine learning concepts to solving the problem. The best approaches so far use what are called symbolic methods to attempt to solve the challenge, and those seem currently to get at best around 80 or 30% of the items solved. I've seen some other reports where the number of items solved is higher than that, but that is kind of what can be seen on the site. And what I'll be talking about today is what I call the ARTI architecture. That's ARTI, which stands for Associate, Retrieve, Train, and Inference. The ARTI architecture, which I have partially implemented to this point, uses natural language processing, semantic search, and test time data augmentation and fine tuning. To start with, the architecture requires two fine-tuned models, a sentence transformer and the long T5 transformer model, which is used for the fine-tuning and inference. These two models are trained on data from the ARC challenge, as well as a variety of generated data and augmented data. The ARC data is converted into a format that is friendly to natural language processing, where the input and output pair is made to be analogous to a sentence. The sentences are used to train what's called a sentence transformer, and the full data strings are used to train the long T former or the long T5 model. The sentence transformer is trained on similar sentences, which are input output pairs that are drawn from the same riddle. And an additional sentence is added to this for the training that is like a negative example, which is not similar to that sentence pair. And the sentence embeddings come from what's called the Distill-Roberta base model. Now I want to talk a little bit about how the solver works. And the first step is what I call associate. Essentially, similarity scores are calculated between all input-output pairs in the data set, and the top 20 items are selected. The colors in these items are shifted to have the same relative color frequency of the current test item. Then new items are created out of each of the retrieved items by taking each input and output pair and making it a test pair. The same thing is done with the current test item. If an item is retrieved from a synthetic data set, new items can be generated similar to this item, or all items can be retrieved from this data set and subjected to data augmentation if needed. The retrieved items and permuted test item are then subjected to data augmentation of rotation and board doubling. Then they are subjected to noise augmentation of 50 noised items each for the item that is not the current test item, and 100 of those augmentations for the current test item. The long T5 model, which has already received much training on ART, is then fine-tuned on this newly generated and retrieved data. And after this fine-tuning, the final answer is received from the model. In the future, I may implement something that is called test time augmentation as another way to improve the accuracy of the results. As I said earlier, I have already implemented parts of this architecture, including the sentence transformer, the retrieval algorithm, and the augmentation functions. I want to go through a few examples to show you what the model retrieves. So if you take a look at the first one, I just have the kind of the training examples for one of the riddles. And so when I run a query on this, the top result is seen on the right. And so essentially the original riddle kind of involves overlaying the top item on top of the bottom item. And the places where there is no overlap is essentially colored red. And what we have on the top result that is retrieved is an item that has some similar dimensions. The function is a little bit different though, in that it's kind of like a rotating and then like a mirror image operation. So then you can see at the bottom where the colors are shifted to the relative frequency of the test item. And since the test item only has 3 colors, I choose some random colors to fill in the additional colors that are needed. So it shifts it some, but there's no way to make it exactly like the test item in this case. So here's another result for the same item, and this one is actually a little bit closer uh, to the original item in that it involves, again, an overlaying process, and where this one, or the other way, is overlaid on top of that one. And the difference being here that the where there is squares from both tiles that are blue are shown as red in the output example. And so in the original, the the ones that show up as red in the output example are the ones that don't have a colored square on both of the squares. So it is, you can see a pretty similar concept. And at the bottom, you can see the colors shifted to be the same in terms of all of the colors. And here is another query, and this is the test item, and this is the top result for that. And at first blush, it seems kind of not related in a way, unless you consider that in a way it's kind of a pattern expansion going from the input to the output grid. So there is like some similarity in that respect. And you can see the colors that are uh, shifted in the bottom example. And so again, the reason to do that is to try to get a data set that is more in distribution. Here's another result on the same board. And this one is, you can more clearly see the pattern expansion, and you go from the input to the output board with adding these expanded squares. And here is another one. In this one, essentially what you're doing is uh, connecting the dots with a line when the horizontal dots have the same color. And you can see in the original example that part of the task is to uh, draw a line in between the dots. Here's another example that part of it involves drawing a line between the bigger shape and the the dots, as long as they are either within the horizontal or vertical plane of the shape. And again, you can see where that would be associated. This one is probably more clearly evident why it's associated, in that you have the dots in the top square, and they are outlined in the bottom squares. And clearly, that is something that happens in the test example. And you can see the example with the colors shifted. It doesn't really do much since all of the colors are actually pretty much the same. Thanks for watching my presentation on the ARTI architecture. Some of you may have noticed that there are some similarities between this architecture and architecture by Google called Retro. There are, I think, also some notable differences. And what I hope to do in the future after completing the architecture and running the full thing is to do another presentation on the results. For some of you who are interested in this kind of a project, I would invite you to join Yannick Kilcher's Discord server, and there is a specific area there devoted to the ART challenge. That's all for today. Goodbye.